You're pushing your local rig to render that perfect, highly detailed asset, and suddenly, your GPU taps out. The culprit is almost always video memory. Generative diffusion models immediately swallow up your VRAM to load massive model weights and output buffers. You can always offload this to a cloud inference service, but running high-resolution generations on external servers burns through indie budgets incredibly fast. We need a practical middle ground. Today, we're mapping out an optimized local workflow that bridges the gap between the hardware you actually own and the production quality you need. Because right now, hardware constraints force independent creators to constantly choose between draining their wallet and shrinking the ambition of their projects. But hardware is only half the problem. The second major bottleneck is figuring out if the changes you make to your prompts actually work. Most solo developers rely on vibes-based testing. You tweak a prompt, run a generation, look at the image, and guess if it feels better than the last one. This creates a massive risk for regressions. You fix the prompt for one specific scenario, but in doing so, you accidentally break the outputs for 3 others. To build something reliable, you have to abandon ad hoc testing and implement a systematic, professional-grade evaluation pipeline. Without measurable evaluation, your local AI project is trapped in a fragile guessing game. You can't maintain a system when you're flying blind. The first piece of our optimized workflow solves the hardware problem. It's a library called Nunchaku, and it brings 4-bit quantization directly to standard Python environments. Standard diffusion models operate at 16-bit floating point precision. Quantization reduces the precision of those weights to 4-bit, shrinking the memory footprint by 75%. This compression happens on the fly, loading the compressed version straight into your GPU. The math translates to massive savings. A full precision model typically demands 12 to 16 gigabytes of VRAM. That same model, quantized to 4-bit, runs comfortably in 4 to 6 gigabytes. Less data moving between the memory and processing cores also improves bandwidth efficiency. A generation that used to take 20 seconds can drop down to between 5 and 10 seconds. Previously, you needed custom scripts to run quantized models. Now, Nunchaku lets you load them through the standard Diffusers API with a single parameter change. This optimization applies across major model architectures, meaning you can use it on everything from Stable Diffusion to the newer Flux models. By cutting memory requirements, quantization turns aging or mid-tier consumer hardware into highly capable generative workstations. But shrinking a model's brain by 75% demands a trade-off. Does it ruin the output? Look closely at this comparison. At a macro level, full precision and 4-bit quantized outputs look virtually identical, preserving the exact structural integrity and character composition. But we need to look closer to see where the compression actually takes its toll. If you inspect highly complex regions like detailed hair strands or intricate backgrounds, you will spot minor texture artifacting in the compressed model. Those minor artifacts rule out 4-bit models if you require pixel-perfect commercial studio renders. But for 95% of indie projects, the quality loss is practically invisible. With the hardware savings secured, we have to fix workflow reliability. We do that with a lightweight framework called Smevals. Smevals replaces vibes-based testing by forcing you to define strict input prompts and exact criteria for what a successful output looks like. The tool splits your prompt against all your test cases, giving you a definitive pass or fail for each. Unlike heavy enterprise tools, Smevals is inspectable, running locally to expose the raw scoring logic underneath. Because you can see the code, you have total control over it. You can adjust the strictness of the tests for the specific needs of your project. There is a reality check here. Instead of instantly generating images, you have to invest significant upfront time writing this custom scoring logic. But the initial hours you lose writing test criteria will save you days of headache later. You catch regressions immediately, long before they ruin your project. Let's zoom out and look at the absolute hard limits of this setup. This entire pipeline, the 4-bit quantization and the lightweight evaluations, is strictly designed for inference. It is for running models, not making them. If you want to train a foundational model or fine-tune an entirely new art style from scratch, there is no shortcut. You will still require heavy, full-precision hardware. But if you stay within inference, the broader benefits of a local pipeline are immense. Keeping all your prompts and generated data entirely on your own machine guarantees absolute privacy. You also drastically reduce your environmental footprint and personal energy costs by utilizing the hardware you already have, rather than constantly pinging massive cloud GPUs. You might not be able to train models from scratch, but mastering local inference gives you a highly secure, sustainable, and cost-effective development environment. This chart lays out our optimized workflow. Combining hardware efficiency with rigorous testing locks us into the ideal balance of low cost and high reliability. If you're a solo creator building assets on a budget, this 4-bit and Smevals stack is exactly what you need. If you operate an enterprise studio where a single compression artifact in a commercial final render is unacceptable, skip the 4-bit inference and stick to full precision hardware. AI tools will not do the hard structural work for you. They only amplify the logic and the boundaries you set for them. Transitioning from merely playing with AI to building rigorous, reliable systems is no longer a matter of your hardware budget. It is a matter of your engineering discipline.